So here's, in a schematic, this is what we call a reaction where we show the free energy, and these are the state diagram. And here's the initial state, is the final state, and basically what I've said is that for something to go from this to this state, final state, there has to be a decrease in the overall Gibbs free energy. But usually what happens is before it can go through that, there is a barrier that it has to overcome, and this is basically called an activated state, and this determines the kinetics. In other words, the system has to have overcome this energy barrier, and then there's obviously a net release in energy, but this determines the kinetics. So so here's the local minimum. So basically, every time we look at a transformation, the first thing I always ask is, okay, what's the delta G, which is the final state, that has to be less than 0, and then if I want to know how fast things are, I have to know this term. So let me give you an example, a relatively simple example of this, illustrating the concept of transformation and kinetics. If you put amorphous silicon on aluminum, so this is amorphous silicon, this is aluminum on silicon, right? And you heat it. All of a sudden, and after some time, you find that the amorphous silicon has disappeared, and the aluminum has come to the surface. And you say, what happened? You say, well, you know what? Maybe the silicon dissolved in the aluminum. But then somebody says, no, but the solubility of silicon in aluminum is very limited. It's only 1%. And yet this thickness of silicon is far more than 1%. So what happened? Well, basically, if you were to then strip the aluminum off, you'd find that the amorphous silicon has actually gone and formed an epitaxial layer on the crystalline silicon below. So what was the driving force here? Can anyone tell me what the driving force? Why did this? Obviously there's a transformation has happened. So what? As I said, there has to be a negative free energy. So what does that imply? It basically says amorphous silicon has a higher energy than crystalline silicon. So give it a chance, it will transform into crystalline silicon. Now, why doesn't it do it by itself? Well, once you have the aluminum, what the aluminum does is it actually acts, it breaks up the silicon dissolves, and then it diffuses. So this is there's a kinetic barrier, but it actually helps it by breaking up the silicon, allowing it to diffuse, and then allowing it to go into the natural state. So if you were to deposit amorphous silicon on silicon, if you raise it a high enough temperature, eventually it will crystallize. So it will go through a transformation. What the aluminum does is that at even lower temperatures, it breaks it up. Once it breaks it up, it's now given a pathway, and then it forms. So you've created a transformation. The kinetics now is decided by the aluminum, and it's the diffusion of the silicon and aluminum that decides. And I'll give further examples of these. So here's just some things, and I won't go through any much detail, but basically in most cases, when this is very low compared to RT, this is the rate. So in other words, rates could be very low if delta G is very small. But if delta G is very high, then basically what it's saying is that you could have a very strong driving force, but if the kinetics is going to be determined, whether the transformation occurs is determined by the kinetics. And so in many cases, right, when we look at a lot of the reactions and we want them to happen in real time, we have to look at the kinetics, and this is where sometimes we talk about using a catalyst, because what a catalyst does is it will change this number and make it smaller, so you don't have to. So one way to obviously increase the rate of reaction is always to go higher in temperature, right? And in most of the silicon processing, that's what we've done in the past. We've always raised the temperature whenever we wanted something to happen. But in many cases, we've got situations where the transformations or the depositions or the materials underneath can't stand those temperatures. So then you have to figure out ways, how do you actually reduce this? You can reduce by catalyst. And I'll give an example of that when we talk about the high K metal gates. So that was all you had to know about materials. As I said, Only thing you need to know about, what's the driving force, what's the kinetics. And all the engineers who've always worked for me, they'll always joke that every time they would come and give me a result, I'd ask them the same two questions. So they always were prepared to answer that. The next thing that is important is about defects and electronic states. So here I'm showing say like a metal oxide, right? It's sort of transition metal oxide that is used in high-K metal gates. And it's arranged in a lattice. You have the metal atom and you have the oxygen atom. Now, usually they're organized in a very nice lattice, and you know from your solid state theory that as a result of this, you will get bands. The orbitals that are associated with each of the metals will be separated and then broadened into bands. And depending on the system, you could either get a band gap between occupied states, or you could get them overlapping, and you would determine the electronic state. But in real life also, what happens is that you could take one of these oxygen atoms, say for example, it could be freed either from a chemical reaction, a ion implantation, some other thermal effect, and the oxygen then is separated. You form what we call a Frankel pair. So there's a oxygen vacancy and an interstitial that comes right over here. So these have to be actually treated. They're real properties. So just like I was talking about elements being part of, you actually treat these as components of overall system. They have a free energy associated with them, and typically what will happen is that you can sort of, in many cases, just look at these as being the components that move around and change and create a lot of the changes in the property. And in fact, some of the new devices take advantage of this fact that we can create all sorts of new properties just playing around with the number of defects and their arrangement. So they are real entities, and they are realities associated because of the crystal structure that exists, or actually to some extent of the bonding. Now the toughest part always is that we sort of infer. They're sort of like, how do I put it? I mean, the evidence is always circumstantial. It's very hard to see a vacancy. Typically nowadays we are seeing them in some, from really high resolution TMs. So their thing is inferred based on what we understand of the impact of the property. So we look at like leakages, we look at electronic properties, and based on that we say, yes, you know what, these are the vacancies. So that's always the tough part. So here's, for example, in a hafnium oxide, this was a two-dimensional, this is a three-dimensional figure of, and I always have a hard time trying to, so there's supposed to be these are the hafnium oxygen, there is a oxygen vacancy here, and there's an extra oxygen interstitial here, and then we can actually do a lot of ab initio simulations, and because these defects are, you can think of them as a perturbation of the ideal crystal structure, they have an electronic state associated with them. So basically the lattice itself gives rise to a band gap, electronic band gap, and the defects themselves create traps or create energy levels within the band gap, and that impacts a lot of the electrical properties. And so again, what is required from the material side, because at the end we are talking about electrical devices, whenever we talk about materials, yes, we want to talk about transformations, we want to talk about what happens, but in the end we still have to talk about electrically what is the impact of them. Does it increase leakage? Does it do something else? Does it change the threshold voltage? And that's the tough part, and this is where, like, we always talk, everything becomes interdisciplinary. The electrical engineer has to know enough about the materials, and on the material side, really the materials person has to really be able to state, with this material transformation that has occurred, what do I expect to happen on the electrical property side. So let's use some of these materials concepts that we've learned for devices and processes. I talked about some of the the evolution, and you've probably heard a lot of details about transistors. I'm assuming that's right. And so I'm not going to go into details. I'm just going to talk about the materials processes that come into play and how they impact the performance. So I'll talk about high K gate oxides. I'll talk about some properties of the metal gates, and to illustrate some of what I was talking about thermodynamics and kinetics, I want to talk about the interlayer growth that occurs in some of this, and then we'll talk about some of the processes, gate first, gate last, 3D structures and contacts, to illustrate how we use materials to achieve a certain electrical property that is needed. So first and foremost, right, why did we need high K materials? As we talked about, for the longest time we can think about, it was silicon and silicon dioxide. So we had the polysilicon dioxide gate stack. The SiO, here we can see a high resolution TEM. These are showing the crystal lattice of the silicon. This is the crystal lattice of one of the grains of the polysilicon. The SiO2 is amorphous, and it's 15 angstroms. And for many generations of technology, all we did was scale down this SiO2. So as I said, you probably heard from some of the device talks, it was also about lateral scaling, and scaling of the gate oxides was a big factor in continuing to shrink the transistors and still maintain the performance. The problem is that as you decrease the thickness, so we are looking at the leakage, the actual leakage when you apply a voltage across a silicon dioxide, and you look at here's the gate voltage and here's the current, and this is the thickness. As we start reducing the thickness, as we start reducing the thickness in this direction, this is 2.5, I can say this is 1.5, the leakage numbers start going up quite a bit. And these are the leakage limits for DRAM, for low power, for some of the higher performance. So the DRAM, for example, you can't have leakage. The moment you have leakage, you can't hold the charge, right? So they were the first ones to actually look at ways to replace the silicon dioxide. These leakages are due to direct tunneling, so there's nothing you can do in terms of from the properties of the material to be able to change that. These are fundamental properties of the oxide, right? So the key issue is that the physical thickness, because they're tunneling, they're determined by physical thickness. So then you say, okay, fine, right? If I want to reduce the leakage, I need to have an insulator which has to have a minimum thickness, say about 20, 30 angstroms, right? That way I can keep the direct tunneling down. But then if you have a very thick oxide, in many cases you're looking for capacitances, and capacitances are inversely proportional to the oxide thickness. So the only way to do it is to then have a high dielectric constant, and that effectively that increases the capacitance, and it's like effectively decreasing the electrical thickness of them. So people started looking at all the transition metal oxides. You can find things all the way up to tioxide and even to like ternary oxide STO, which have like dielectric constants of like more than 100. The problem is that as you increase the K, which you want the highest K possible, the band gap of those oxides starts to decrease. And the problem is, as you decrease the band gap, then you reduce the barrier to silicon, and so now you can actually have electrons from the silicon hopping over the barrier, going into the oxide, and then going onto the electrode. So your leakage again increases, not because of tunneling, but because you can't maintain enough barrier. So what happens is that you wind up saying, okay, I need to have a band gap to give me enough margin, somewhere around 5 to 6, and you wind up with then things which are hafnium oxides, lanthanum oxide, and then eventually everybody moved into hafnium oxide. So it's a question of like, this is the K is too low, but the band gap is great. That's for silicon dioxide. You go over here, the dielectric constant is high, but the band gap is low. So you have the Goldilocks effect, which is just right, right? hafnium oxide, right? Just the right band gap, right amount of K allows you. So this is what you wind up with is the hafnium oxide, and then it turns out initially when they introduced the hafnium oxide, they tried to integrate it with polysilicon, but there was a whole lot of issues associated with charge states and other things that were created at that interface. Besides, the polysilicon also had depletion effects, added extra capacitances. So people at once went to the metal, and so that was the origin of the metal hafnium oxide, high K metal gate stack. And if you look carefully at this figure, you will see that not only do you have hafnium oxide, but there is this layer here which is really silicon dioxide. So whenever you have the transition metal oxide, there is some interlayer oxide that is there. Now it turns out that that oxide, so here's what if you look at a high K metal gate stack in many of the devices, this is what we have. We have a silicon, we have an interfacial SiO2 layer, we have a high K layer, there is a very thin metal layer which determines the work function, and then there's another layer that is placed on top of it, which is basically for other purpose for conduction, etc. And this interfacial SiO2 layer, you'd say, okay, and the strange thing about this SiO2 layer is that you'd say, okay, well, that probably came as a result of my cleaning process. I took the silicon, I cleaned it, but I grow silicon dioxide right away. But that could be like 5 maybe to 8 angstroms or so at best. But in many cases, this would be much thicker than that area. It could go up to as high as 25 angstrom, which takes away the whole benefit. So I'll come back to this question about what drove. So again, if somebody came and told me, I put 8 angstroms, I put the hafnium oxide, I'm quite sure I still had 8 angstroms of oxide, and yet after I put the metal gate and I went through anneal and I came back, it's like that 8 angstroms became 20 angstroms, right? And I would ask, what's the driving force and what's the kinetics of that, right? We'll get to that. So as we talked about, let's go back and think about it. I told you there's this work function metal, right? So the nice thing about the polysilicon, let me go back again. I didn't quite. So the nice thing about polysilicon when you had N and P channel is you could dope the poly N or P and change its work function by changing the doping level. And you really need that for the N and P channel, because for the N channel, you really need a work function about 4.1 eV near the band edge of silicon. And for the PFET, you need something which is like 1.1 eV, so you need 5.2. And I said, if you used N plus poly and P plus poly, you got that, but you can't use N plus and P plus poly here. So really, you had to go back and start looking at all the metals, right? Now, thankfully, people had been looking at work functions of metals for many, many years. It's something you look at all the time in physics. So, but all of a sudden now, in earnest, you got to start looking at it for. So here's from a paper from way back in the 60s, where they looked at all the work functions of all the elements in the periodic table, and the ones which had the highest were things like platinum, palladium, rhodium. Platinum is here, it's about 5.1, 5.2. But you know what? You're not going to put platinum if you want that, you're not going to put it in a device. It's too expensive. And then on the other hand, if you want 4.1, there's quite a few that could, but then there have to be metals, right? So aluminum has the right, maybe tantalum, titanium also. But then you have to make sure that they are stable in contact with the high K metal gates. So that's the other problem. Even if you get the right function, can you make it stable? So if you just took elements by themselves, first of all, there's either a cost issue or there's a stability issue. So then the next thing is, okay, you know what? Why should I always look at elements? Why don't I look at compounds, right? And when you start looking and you start thinking about what work functions happen, it turns out that there's a rule that you can look at that the work function, if you have a compound, it's sort of determined by the net electronegativity. You can take the average electronegativity. And so if you add, like, for example, if you want to increase the work function, so in other words, the work function increases with electronegativity. So if I want to have, if I took titanium and I add something like nitrogen to it, right, I can increase the work function, which is what happens. Titanium has 4.1, titanium nitride has 4.5. And in fact, if I start increasing the amount of nitrogen, I can improve it. Same thing with moly, right? I can improve by adding moly. Now, what's more electronegative than nitrogen, for example? Anybody can guess? Something to wake you up? What's one of the most electronegative elements in the periodic table? Huh? Chlorine, yeah, you could have chlorine, fluorine, well, oxygen, right? So the other issue is that you want to have an element that basically keeps the, you want it still to be metallic. So the problem sometimes is that you take an oxide and yeah, sure enough, you would expect its work function, but then it's not a conductor, so it's an insulator, so it doesn't work. But you could add oxygen in some of the cases, enough oxygen, and still keep it, to be. So like ruthenium oxide, for example, is metallic. Some of moly oxide is metallic. So in the case of moly, you can add oxygen. You can see that all of a sudden you can vary. Then you can add carbon on the other side, right? So carbon is less electronegative. In fact, let's see, these are all relative to the tinitride. So people are looking at hafnium carbides, tantalum carbide, carbides. They're conductive, and they have the work functions that bring you close. So now all of a sudden we are looking not only at different elements, we're looking at carbides, nitrides, oxynitrides, name it, you got it. Now fortunately what happens is life sometimes gives you a lot of breaks. When we go from planar bulk to 3D devices, the requirements for the work function actually decreases. We need a smaller range. It ranges from 4.4 to 4.8. So in some sense, what has happened is at the planar side, you've discovered all these work functions that you need. Then when you come back to the FinFET, you find, what, it's not as bad as you want as it. So that's good. Now let me come back to this. I talked to you about the silicon interlayer formation, right? So what people noticed was that they'd start off with some oxide at the interface, and the moment they put the metal gate and went through an anneal, the interlayer thickness would increase. And this is showing, like, if you look at the partial pressure of oxygen and the temperatures, that you could actually get up to, even at 450 degrees, you would get like 33 nanometers, 30 angstroms of growth of oxide, 450 on. And this was explained by Guha and Narayan in IBM. What they pointed out, and I'll come back again, is a question of what is the driving force, what is the kinetics. It turns out that the process consists of the oxygen in the ambient, right? There's a metal electrode. The metal electrode breaks up the oxygen into oxygen atoms, and then the hafnium oxide has these oxygen vacancies. The oxygen, the vacancies, the oxygen combines with the vacancies and actually diffuses through the hafnium oxide using the vacancies, or you can think of the vacancies as moving up. And then when the oxygen comes at the silicon, it reacts with the silicon, forms silicon dioxide. And then in the process of removing an oxygen from this hafnium oxide, it creates a vacancy, right, which then is moving up. So you've got this continual cycle of vacancies moving up, oxygen moving down. So it's almost like a fuel cell, but the source of the oxygen is from outside, or in many cases, even if you cap it off, it's the oxygen that is in the electrode. So there are two things that I had. The driving force is really the fact that the chemical potential, if you take of oxygen outside, is close to zero, because that's the standard. The chemical potential of oxygen in silicon dioxide is negative, because you have a heat of reaction. So there is a strong driving force for the oxygen to come over here, right? You normally don't see it even when you're heating silicon in oxygen at 450, because the kinetics are very slow. What the hafnium oxide does, actually, it acts as a catalyst. So it's not only providing a medium, but it actually changes the reactivity and allows the reaction. So you've actually reduced the delta GA needed. So the delta G hasn't changed, the delta GA that changes. And in fact, I want to show like this whole issue of silicon dioxide growth. It's a classic case, which is studied back in the time of Deal and Grove, where they looked at it's a rate limited step at when you use initially, and then it becomes diffusion limited. So for example, we've always looked at the oxidation of silicon and atmospheric oxide, and you usually typically have to go to about 700 degrees to get any appreciable reaction rate. So it's really limited by the dissociation of oxygen on the silicon surface, and then once you get above a certain thickness, it's limited by the diffusion capability. And silicon dioxide is a good barrier to oxygen. You have to go to relatively high temperatures to have it diffuse, so it'll stabilize out. However, if you now have active oxygen, you can actually improve the rate limiting step, and you can start growing oxides at 400 degrees centigrade. And I believe one of your students, or I think Professor Nishi's student, were looking at plasma activated oxygen at low temperatures, I believe, right? I mean, if you have a remote plasma, you can get this active oxygen which will react with silicon at low temperatures. So you basically get over one of the barriers, which is now of course once you get a certain thickness, then you get limited again by the diffusion coefficients. And here the final case where I've talked about, where you can be around 300 degrees, or even sometimes at 260, and basically what you've done is that you've got a source of oxygen in the metal, and you've used hafnium oxide as a catalyst, and you grow this silicon dioxide as low as 300 degrees centigrade. Now here's the trick. So here the thing has been, this is the source, this is the sink. So now people saying, well, if you grow too thick an oxide, you've basically taken away the whole advantage, right? Because the whole idea was to have as thin a silicon dioxide as possible. In fact, the way to think about this system, which I've showed about, is you're still carrying, you always need some level of silicon dioxide, because you get the best mobility and you also get the best reliability. So you almost need like 3 to 5 angstrom of SiO2, and you're sort of adding the high K metal gate to add some physical thickness, but you're in effect scaling. Everything is being determined by that silicon dioxide. So you need it, but you don't want it to be very thick. So if you're even starting, you can start off with 8 angstroms, when you just clean it and put it in. So you can say, hey, you know what, how about I make it go the other way, right? How about I make this a sink and this a source? That means you have to think about materials whose oxide formation energies are much lower. In other words, they are much more reactive, and they can reduce SiO2, right? So all of a sudden you can take, and you say, okay, supposing now instead of my metal being a source of oxygen, how about I put some what they call scavenging metal, and so it could be like aluminum, titanium, that have much lower formation energies than SiO2. And then what they do is they actually act as a sink, and now the SiO2 is acting as a so here are some things just showing that even at 600 you start off with if you have a regrowth, now you have just the opposite. You reduce the oxide that you started out with. And here's the case, like before anneal you had 0.82, 8 angstroms, and you could reduce it down to 5 angstroms. And in fact, if you put enough, you can reduce this to 0, but you don't want it to reduce to 0, because then you have a lot of problems. So all of a sudden, if you know the material science, it's like, okay, I know how to go and modulate and modify things to achieve what I want.